Yep. So do we have any questions about how to pass parameters to a subroutine and how to pass a return value from a subroutine back to the caller? No questions? Okay. Just as a really quick reminder, the way we pass parameters is to have the caller to push the parameters in the reverse order on the stack. What that means is the last parameter is pushed first. The first parameter is pushed last. So the effect is the first parameter has the lowest address of all the parameters. After all the parameters are pushed, then we push the return address, and then we jump to the subroutine being called. So that's kind of the agreement between the caller and the callee. When a subroutine has a value to return, then it is being returned by register A by convention, okay, with this processor. Most other processors would also use a single register to return a scalar value. Which register is chosen, it depends on the architecture. So with the x86 architecture, it's usually AX or EAX, as a register. But most architectures have, a particular register they use for returning values. So that's pretty much what we have gone through at this point. We have just gone over parameters on the stack. And now we're going to talk about how local variables are handled. So we'll just kind of talk about it in text, and then we'll use an example to illustrate how we access and how we allocate local variables. Local variables of a subroutine are allocated on a per invocation basis on the stack, much like parameters. In other words, when you have one single subroutine definition, but if it is recursive, then you can still end up with multiple quote-unquote local variables on the stack, one for each invocation. And then the second sentence, however, parameters are allocated and initialized by the caller, while local variables are allocated by the callee, the called subroutine. That makes sense because the caller has no idea how many and what types are the local variables, because local variables, as the name implies, is local to the subroutine. The caller should have no idea whatsoever, how many and what kind of local variables are needed. As a result, local variables have addresses that are below that of the return address, because the caller is responsible to push all the parameters and then the local variable. And then at that point, when the stack pointer is still pointing to the return address, at that point, you have a jump instruction from the caller to the callee. So by the time the callee has control, the stack is already partially set up with all the parameters and the return address. And then at that point, the called subroutine can decide how to use additional bytes on the stack for local variables. Is that okay? In terms of just the concept? Okay. And then the method to access local variables is pretty much the same as accessing parameters. So what we'll do today, to illustrate this point here, is to use a subroutine, and then we'll first write the subroutine itself. Oh, this is really good too. So I'm gonna add to this. I don't think I have used or copy and pasted this into this class notes, but I'll do it with this class as well. Okay. And then here's the callee. So the callee is solely responsible to allocate and deallocate local variables on the stack below the return address. Okay, I'm maintaining a set of agreements between the caller and the callee. So this way, when you need to write a subroutine that is to be called by some caller, you know what you can assume and what you cannot assume. Okay, so just remind me to copy and paste this when we are done with today's class. So I'm just going to save it into the cisp310 subfolder. We'll call it caller callee agreement.txt. It's just a text file. So now let's go ahead and take a look at a subroutine that you probably have seen many, many times over, but we'll go ahead and see how we can implement it in assembly language. So the subroutine is called swap, or exchange, you can call it either way. So in this case, let's make it clear that we are exchanging 8-byte or 8-bit integers. So this is a pointer to the first one, and here is a pointer to the second one. So pointer A and pointer B are pointers to unsigned 8-bit integers. So inside the subroutine swap, okay, there are many ways to do it. One way to do it is to have a temporary variable, we'll just call it t here. So t is going to get whatever ptra points to. In other words, I am just saving what ptra points to, saving the content pointed to by ptra. And then I can change whatever ptra points to whatever ptrb points to. So I'm copying whatever ptrb points to overwrite whatever ptra is pointing to. And then I can change whatever ptrb points to t, which was the actual original content of whatever ptra was pointing to. So this is a pretty typical sequence of exchanging the values pointed to by two different pointers. Are there any questions about the subroutine in C? So are we doing okay so far with the subroutine in C? Okay. So to utilize this particular subroutine, okay, we'll just have a kind of useless main subroutine here, and we'll just say declare two variables, okay, a and b in main, and we'll say a equals to 16, b equals to I don't know, 11, okay. So this way, a and b have some kind of initial value. I can test whether those values were actually exchanged in the end. Then I call the swap subroutine and say, okay, let's pass the address of A and the address of B to the subroutine so that the content pointed to by these addresses can now be exchanged. And that's the entire subroutine. So do we have any questions about this program in C form? Okay, no questions about this one in C? Okay. So the question now is, how do we implement this in assembly? Okay, because that's kind of difficult now because we have just started to talk about local variables, and yet in this program, main has two local variables, A and B, and then swap has one local variable T. So now we have to kind of think about, well, how do we do this in assembly? So we'll go ahead and use a new window on the side so that we can keep an eye on the C code while trying to work out the assembly code. The first thing we do, as usual, is subtract D from D. And this is really just to initialize the stack pointer. And then we have main colon here. This is really just for documentation purposes. Nobody's going to call main. So this is really just a label to designate, yeah, this section of code corresponds to what we know as the C main subroutine. But it really is not a subroutine. This main is not going to return. There's no place for it to return to. Okay, so it would just be ended with a halt instruction. So I might as well just write a halt instruction right now. So this way I don't forget to put a halt instruction at the very end. Okay, now what do we do? Well, we got two local variables, A and B. So we're going to have to allocate the space for local variables A and B. Now, as local variables, A and B are not initialized, which means, well, I mean, you can put the initialization here, but if I were to stick with the actual C code, then these two are not initialized local variables, which basically means I just need to save some space on the stack for these two local variables. So how many bytes do you think I need on the stack in order to store A and B as local variables? So 16 bits, which will translate to 2 bytes. Okay, very good. So we need 2 bytes. And I just realized, registers also have A and B. So we'll change A and B here to something else so that we don't accidentally, X, Y is the same. We'll call this, okay, this is, I'm running out of good names for this. So we'll just say var1 and var2. Because I just don't want to confuse people with the registers. These are no longer registers. They are local variables. Okay, there we go. All right, so there we go. All right, so we need to save 2 bytes on the stack. or allocate 2 bytes on the stack without actually specifying the content at that point. So one way to do it is just to say decrement D and decrement D. Okay, so we are now save space for var1 and var2 as my local variables. They are on the stack. What are the current values of var1 and var2? I have no idea. Okay. Now, if you assume that we have just done a control R with the simulator, then they have initial values of zeros. Yes?
Can you explain decrement D line 3?
It decreases the value of register D by 1. That is also explained in the opcode table. Okay. All right. So now that we have saved 2 bytes, we kind of need to know which one is var1 and which one is var2. So sometimes, or most of the time, it helps to kind of have a picture of what is on the stack. Okay, so it's up to you. Do you want var2 to be the one that is on top and var1 to be the one that has a lower address? That's up to you. But whatever you decide, it has to be consistent. When you work through the code of this program. Is that okay? All right. So I'm just going to go with this particular order, which means the first variable declared has the lowest address. Okay, I'm just using that particular rule. Okay. So the next thing we do is we have to somehow initialize those those local variables with specific values. So now what do? Well, we could use register D, but I don't want to mess around with the stack pointer. The stack pointer really should not move around unless you're ready to allocate or deallocate things on the stack. I'm not trying to do any of that. Okay, I just want to go to certain locations on the stack and initialize those locations with specific values. So I'm not going to use the stack pointer. Instead, I will do a CPR CD, which effectively is just saying register C is now the same as register D, which also means, okay, whatever register C is pointing to is var1 at this point. Is that making any sense? Now, there's one more way to put it. Okay. The other way to put this is C is the address of var1 at this point. Are we doing okay so far with these documentation? All right, well, since C is already pointing to the right place, I just need to put a value of 16 to the place that is pointed to by register C. I can't really save another, I have to use another register for this purpose. LDI A16 is kind of needed. And then we can do a STC, not D this time, from register A. And somebody may say, but register D is still pointing to var1 at this point. Yes, it is. But because register D is the stack pointer, and the stack pointer can quote-unquote move around a lot, we are not going to refer to the stack pointer. Because next, what we need to do is to go like, okay, now that var1 is initialized to 16, what about var2? Okay, so I'm going to just put here and say that this is doing the job of var1 equals to 16. So in order to get to var2, I'm just going to do this, increment C. So now C, whatever C points to is var2, or you can say C is the address of var2. Do we have any questions about this step here? Register D stays constant, okay? It's not moved, okay? We are not allocating or deallocating anything on the stack. I'm just using another pointer, register C, to move around in the stack so that I have access to things that are already in the stack. Is that okay? So now, the next thing is LDIA with 11. And then we do another STC, but this time C is pointing to var2, which means this is going to perform this particular operation in C. Are we still doing okay so far at this point? So now that I have initialized both variables in the C program, in other words, we are now down to line 13 is done. Okay, we are moving on to line 14 at this point. So line 14 says, okay, we have to call a subroutine swap. But before we actually jump to the subroutine, we have to set up the parameters and also the return address. So we got 3 things that we have to push on stack this time. The first thing we need to push on the stack is the last parameter, because that's the convention. The last parameter is pushed first so that it has the highest address of all the parameters. So in this case, the last parameter is the address of var2. Well, guess who has the address of var2 already? Register C. So very handy, huh? So we just have to decrement D this time, okay, to allocate for second parameter. And then we can now immediately store to whatever the stack pointer points to, whatever C has, okay? So this is basically just pushing the address of var2. Okay, what about now? Well, we need to push the first parameter now, which is the address of var1. Well, the address of var2 is really just 1 more than the address of var1. So that means in order to calculate the address of var1, what is the easiest way to get to it? Decrement C, exactly. So we just have to decrement C. Okay, I'm just commenting here because C is now the address of var1, and we just need to push it. But in order to push something, you have to first allocate the space on the stack. So allocate for the first parameter, and then we can now store register C to whatever the stack pointer points to. So that accomplishes the pushing of var1 on the stack. So now we got both parameters pushed on the stack. The last thing to push is the return address. So we just say LDIA with main return, define main return right here. That's just usually the way I do things, so I can go back and backfill things later on. And then we have another decrement of D. We are now allocating space for the return address. And then do another std, store to whatever register D points to, the content of register A. So this basically pushes the return address on the stack. So now we have all 3 things that we need to push on the stack. It's time to jump to the subroutine. So we have a JMPI to swap, because swap has the same name as the subroutine itself as a label to mark the beginning of the subroutine. When we come back, we got one thing to do. We have to deallocate the space used by the parameters. So we can say increment D, and these 2 increments together is to clean up after the parameters of the call. But because this is also reaching the end of main, technically speaking, we should balance the stack. What things are still on the stack at this point after the last increment D on line 23? The variables, very good. So the local variables are still on the stack right now. Do we need it? Because we are now at the end of main. We don't need it, right? So to emulate the returning of a subroutine, we need to clean up that as well, okay? So we'll do another increment, or another pair of increments, and these 2 are for cleaning up after the local variables. So are we doing okay so far with the 4 increments? Now what if we don't have any single one of these increments? Instead we just halt, okay? Well, the program will still halt properly, okay? The content of those 2 locations will still be swapped correctly. However, conceptually, the stack is no longer balanced. In other words, by the time we get to the halt instruction, the stack there are still 4 bytes in use on the stack that should not be in use anymore. Is that okay? It's kind of like walking out of a bathroom not flushing. Will somebody actually see you and fault you? Maybe not, okay? But it's still not the right thing to do. So this is still it's still a good thing to clean up after the stack, even though the only instruction after that is just a halt instruction. Is that okay? All right. All right, so that takes care of main. What about swap? Okay, so now we work with the swap subroutine. So the swap subroutine is up here. So by the time we get here, the swap subroutine would have the following on the stack. It would have it would have PTRB being on the highest location on the stack, PTRA right below that, the return address right below that, and the register D or the stack pointer is pointing to the return address right at this point of time. Is that okay? That is because of the agreement between a caller and the subroutine being called. So this part is guaranteed. But when I look at the code of swap, I go like, line 3 says that we need a local variable called t just for the swap subroutine. Okay, so let's go ahead and allocate for that. So now we decrease the stack pointer by 1 to allocate for local variable t. So that means, in terms of the picture of the stack, okay, so I'm only going to do this like one more time, because otherwise the program gets kind of big because of all of these comments that are in line. So at this point we have local variable t on the stack, and it is now being pointed to by the stack pointer. Are we doing okay so far? Now t is not initialized at all at this point, because all we did is to allocate we allocate a byte for local variable t by only changing the stack pointer. We did not go back and say what should be the content at that location. We simply said, let's save 1 byte here. Okay, so now we're done with all the initialization at the beginning of swap. The first thing we need to do in swap is the right-hand side of the assignment statement, which is to figure out what PTRA as a parameter is pointing to. Okay, so now we have a few things that we have to do. I don't want to mess around with the stack pointer. Okay, so as usual, we do a CPR, whoops, wrong window. We do a CPR CD, okay, so that now C is the address of what? Yep, C is the address of the local variable. But that's not what I want at this point, okay? Eventually, yes, I need to get back to that later on, but not right now. Because right now, I need to dereference. On line 4, we need to dereference point PTRA. Well, let's see how we can get to the address of PTRA first, because we have to get there. So if you look at the address of T, and then you look at the address of PTRA, they're off by 2 bytes. Okay? So the quickest way to increment D by 2 is increment twice. Okay? It's faster than loading 2 into register A and then add it to D. Okay? Even though both are 2 instructions, this one is actually faster. And it also saves 1 byte in terms of opcode. Huh? Oh, you're right. Increment C. Yep, you're right. Thank you. And as we increment, we can also document what C should be pointing at. So at this point, it will be pointing at the return address. And after this, C will be pointing at what we want, which is the address of PTRA. Is that okay? Okay, cool. PTRA sounds like something that we need. But C is the address of PTRA, not what PTRA is pointing to. So that means we need to first dereference register C to get to PTRA itself. Okay? So we can use a load instruction. I can use any register other than C because I kind of want to keep C around for quite a few things. So we'll just say that, LDA with C. Okay? So the effect is A is whatever C is pointing to, and that turns out to be PTRA. Let me use double equal here because we are not doing the assignment. We are just stating the result of this particular operation. Is that okay? Because this is where things get a little bit kind of complicated, because it is really important to keep track of who has the address of what. Okay? C has the address of PTRA. So by dereferencing C, now A is PTRA. But wait, PTRA is not what we want on line 4. Okay, it is a means to get to what we want, but that is not the thing that we want. We want what PTR A itself is pointing to. So we need one more dereference at this point. Okay, so we now say, you can definitely do this. That's fine. Okay, it works. So after this, A is now whatever PTR A is pointing to. Phew. Okay, now we got the right-hand side of line 4 done. And now we can move on to the left-hand side of line 4. In other words, we need to store this back to local variable t. Well, who is still pointing to local variable t? D. Okay, well, that's kind of nice. So we can now say st indirect to d, a. So this is effectively saying t gets the value of whatever PTRA points to. So we are now done on line 4. Do we have any questions about how line 4 was implemented? Are we good so far? Okay. Well, if this is done, let's move on to line 5. So you look at line 5 and go like, oh, not this kind of stuff again. Well, yes, it is. Okay, but we can do it. We just have to do it step by step, starting with the right-hand side of line 5. So the right-hand side of line 5 is we need to know what PTRB is pointing to. That means we have to get to PTRB first. We have to know the address of PTRB. So the last time we did something to register C, it was the address of PTRA. And then when you look at the address of PTRA, it is only 1 byte below the address of PTRB. Well, sounds like it's relatively easy to get to PTRB, or the address of, so increment C will do it. Okay, so C is now the address of PTRB. Did I make a mistake? Oh, I wrote increment D. Yep, sorry about that. Okay, there we go. Now that we get to the address of PTRB, we'll do the same trick as before, LDAC, so that register A now has the parameter PTRB, which is a pointer. And then we have to do it one more time, LDAA, so that A is now whatever PTRB is pointing to. This becomes the left-hand side, the right-hand side of line 5. Is that okay? So now we have to go back. I didn't save anything into register B. I could have done that. Okay. So if I don't want to recalculate the what PTRA is pointing to, I could have saved it, with a CPR when we got here. Okay. In other words, I just need PTRA back again, which means when A is PTRA, I could have made a copy and just say CPRBA. So that now register B, so I always comment and say register B is also PTRA at this point. Is that okay? So now I can go here and go like, oh, since register A has the value of the right-hand side, register B has the address of the left-hand side, then we can just do ST, whatever register B is pointing to, A. That accomplishes whatever PTRA points to, gets whatever PTRB is pointing to. Is that okay? Did you guys see what the meaning of register B is? Because I put CPRBA on line 42, and the line right before that is commented A equals to PTRA, which means B equals to PTRA after line 42. So that B is not used in between. I do not have any function calls, so no one is going to mess around with my register B. So that's why by the time we get to line 48, register B is still PTRA. But I don't want to overwrite PTRA, which is just a parameter on the stack. I want to overwrite whatever it points to. So that's why I need an ST instruction, because an ST instruction can dereference a register and then overwrite the location pointed to by a register. So is that okay so far? All right. And so we are now done with line 5. We are now done. We just need to deal with line 6. So line 6, the right-hand side is relatively easy because the stack pointer is still pointing to local variable t all this time, right? So that means an LDAD is going to retrieve whatever local variable t has. And PTRB is lost because I overrode register A over here, but that's okay because register C is still pointing to PTRB. So I just have to do another LDC, this time with C. So the C is now PTRB. Okay, let's stop here, make sure that we understand why that is the case. Because if you look up the last time we made a change to register C, which is line 45, register C is the address of PTRB. And we did not change register C at all in between. So now, when I do a load C, indirect C, that means I'm dereferencing C to store back into C, which also means I'm dereferencing the address of pointer B to register C. And as a result, C is now the parameter PTRB. Is that okay? Okay. And then after that, we can just do the store instruction, st c, because we want to change the location pointed to by PTRB, which is now in register C. And A is the new content that we want to use because A is coming from local variable t. So now we're done. We're now done with line 6. It's time to return. So when we're ready to return, it's not just those 3 instructions, because the first thing we need to do is to increment D. This time it is actually register D because we want to get rid of the space used by the local variable t. Okay, so this is for deallocating local variable t. Now the stack pointer, okay, so at this point, after this, the stack pointer or register D is once again the address of the return address, which is what we need. So we are going to do LDAD, so that A becomes the return address. Increment D to deallocate register the return address from stack, and then JMP-A to go to the location back to the caller. So that is the swap subroutine. So are we doing okay so far with this code? Are there any specific questions about the assembly implementation of the C code? There's a lot of details to track. Okay. So one thing I would advise, is for you guys to draw pictures. Just draw a picture of the stack for almost every single line of code, okay? Or when it is obvious, obviously this is now changing, something on the stack. But I would just draw a picture for every single line so that you can keep track of what register is pointing where and which one has the same value as what parameter on the stack. Is that okay? All right. So what do we do next? What do you think is a typical thing for us to do at this point? It's not time for the class to end yet. Well, how about we run this code in the simulator? I mean, that's the whole point, right? I mean, we convert C code into assembly code so that we can run it, okay? So we'll go ahead and run this code in the assembler. cisp310. this program is a little bit longer than usual. Takes a little bit of time to assemble. There we go. And then we'll check out, did I make a mistake? Nope. Seems like everything is okay. So we'll go to File, Download as CSV, and then we'll save this one to swap.csv. And then we'll go ahead and start the simulator. Right click, load image, and this one is called swap.csv. There we go. Cool. All right. Well, I can run this thing at full speed and just show you that the locations have changed, but we can also start a trace so that we can actually visualize and see how memory locations are modified and how the stack was being used. So let's do that. Go to logging, and as usual, the program counter is the first one that I need to log because that indicates where are we in the program. Okay, what are we executing? So that's really important. And then we can go into the register bank and look at the individual registers. I know register D is particularly useful because that's our stack pointer. Gotta log that one. Okay. Register C is also useful in this particular program because register C is kind of like a helper. It helps us navigate on the stack so that we can now go like, oh, we need to access that guy, oh, we need to access that guy, and so on. So that's why it is useful. Register A is useful sometimes. It's just a temporary register. So we'll go ahead and log both register A and register B, because that way we have a more complete picture of how the program ran during the whole process. And then there are some RAM locations that are also really useful. So when we look into the RAM locations, we kind of have to start from the bottom because the stack grows backwards. In other words, it grows from the highest location first, and then as we start to use more locations, it can go to lower and lower locations. So now we have to think about, but how many bytes should we watch? Because how many bytes were actually in use in this particular program? There are two ways to figure this out. You can run the program first. Look at how the stack pointer changed over time. Look at its lowest point. That will give you an idea of how low the stack pointer went. And then you can go back and change how many bytes you want to log in memory. But you can also kind of do it theoretically. Main has how many bytes being used? It has got the two local variables, and then it used 2 bytes for the parameters to call the subroutine, 1 more byte for the return address, and then the subroutine itself uses up 1 byte as the temporary variables. So altogether, 6 bytes on the stack should be used in this program. So what I'll do is I'm going to log 7 locations. Just in case my calculation is wrong, at least I can prove that I'm wrong. Then I can go back and track things down again. Okay. So we'll log 7 locations, starting with 255, 254, 3, 2, 1. So that's 5, 6. So only these 6 locations should be changed. Was it 6? Yep. But we'll log 7 just to be sure. Okay, now we'll change the radix to 16. Some, base 10 would make sense in some because we have 16 and 11 as base 10 numbers, but the addresses are typically in hexadecimal, so, and we can convert those relatively easily. Okay, so we'll double check. Yep, so they're all base 16 except for this guy. Okay, I forgot about that one. There we go. Okay, so we got that. And I like to log everything to a table, to a file, because this way it is saved in the system in case Logisim decides to crash. No big deal because everything is in a file. So I like to save it in a file. We'll put it into swap.tsv or tab separated value. Save. And then we can now close this window. And then we do a Control K to run this program. Okay, so looks like it has stopped. And before we go look at the trace, I'm just curious, did it work? So we look at the last two locations here. Remember the lower location is the first variable. Okay, so let me point out which portion we are talking about. Okay, so we have to look at the original C code, and then we look at the memory locations. So in main, var1 is the one that has the lower address. So 10 is 16. 10 in hexadecimal is 16. That was originally here, but now it is here. 11 is 0b, which originally was here, now it is here. So I have some visual confirmation that the program seemed to work the way it's supposed to. I also have some, not definitive, but I have some visual cue that only 6 locations on the stack was used. Because you can count 1, 2, 3, 4, 5, 6. Now I can't really tell whether I overwrote this location with 0, 0, because you cannot see when you're overwriting a location that had 0, 0 with a new value, quote unquote new value of 0, 0. So I cannot confirm that, but it seemed like the program did work the way it's supposed to. Okay? So if the program works, maybe we should just leave it alone, right? No. But that's why we traced it, right? So we can look at the trace. So now we use a spreadsheet, and then we just say, let's open swap.tsv. And I learned this trick. I think I may or may not have shared with this class, but I did share with at least one class, is you can keep everything checked like this. And then what you do is you look at all the standards, okay? So do a shift click so you can select all at the same time. And then click on column type. Instead of standard, change everything to text. So this way it will not attempt to convert the numbers. Converting the numbers is it's not bad, it's just really difficult to read, because 0, 0 translates to 0 and then is right justified. And then all the hexadecimal numbers are left justified and not converted to actual numbers. So this makes it look nicer. Okay, we click OK. And of course, this is our stack pointer. This is register C, register A, register B, and this is location 255. I'm just going to use this notation, whatever 255 points to, whatever 254 points to, 253, 252, 251, 250. And this is the last one that should never have been written to, which is 249. And there we go. And then we'll make the columns only as wide as they need to be, like so. So now we have a pretty complete trace of how this program executed. In other words, this is how you study. Okay, this is how you go through this and try to be able to explain the changes along in the execution of this program. Or the alternative is you look at the assembly code and you go like, I don't know what this line is doing. Okay, this LD, A, comma, C, I don't know what is being loaded here. Locate the trace line corresponding to that instruction, the execution of that opcode, and find out exactly what value was used to overwrite, which location was used to overwrite which register, and what was the value, and then try to explain what that is. So between the C code, the annotated assembly code, and the trace of the program, that should be a fairly complete picture of how that particular program operated. Okay. Is that okay? Okay. All right. So I'm going to give you a gift today. I'll save it. So I'm going to save this one. Okay, I'm going to use ODF. This will preserve the nice formatting of the columns and stuff. Okay. And we'll make a new folder. Okay, 2018. Today is 11:05. So I'm going to save this one to that folder. So that's the trace. I will look at that one. I will save separately. I'll save this one first. So this is the C code, and we'll go to this folder, and then we say this is swab.c. Okay, let's close that, and then we have one more. Yep, this is the one. This is the assembly code. So we'll save this one to the same folder, and we'll call this one swap.ttpasm. Long name, stands for text toy processor assembly file. There we go. The processor I'm not going to save because you guys know how to get that. So now I go to the command line, go to the temp folder, and say zip-r 2018 1105.zip 2018 1105. Back to the browser. Back to this class. And then I'm going to give you the file. So my browser, there's not enough screen space to see the entire thing. There we go. And this is temp 2018 1105.zip. Okay. Item. There we go. So this is the zip file that contained the three files that are kind of useful. The first one is swap.c, which is the original C code. Then we have swap.ttpasm, which is the assembly code corresponding to that C code. And it's fully annotated. Okay. And then we also have the trace so that you don't have to run the whole thing and then trace for yourself because the trace is already done. So I'm giving you a copy of the trace as well. So I would consider this studying material. One thing you can do, okay, with this one is the first thing you get with the TTPASM file is to remove all my comments. Okay, just strip all the comments that I have made and then try to annotate that file yourself to figure out, okay, what is this line, what is this line doing? What is register C pointing to? What is register A pointing to? What is in register B at this point? So see if you can track down all of those things, and then you compare your version with my version. Do you want me to kind of strip it myself and then give you guys the stripped version? I don't think anyone in this class has photographic memory, but is that okay? Do you guys want me to do it? Okay, sure. Okay. So, all right, so to do that easily, I'm going to use a program, 2018 1105. This is swap.ttpasm. Okay, so the quickest way to do this is to use Vim, because Vim allows me to specify // which means / and everything after that, replace it with nothing. So that would get rid of all the comments. I really like VI. It's the ability to use regular expression that gives me the ability to do something like this. Okay, so this is all script, and we'll save it as a different name. Like so. And because the zip file already contains the doc and the annotated one, I'm going to upload this one separately. So we go to File, New File, and this one is 2018 1105, and just the stripped version. Yep. There we go. So kind of disorganized because I'm giving you both the zip file and also the, uh-oh, that didn't work, did it? Where did it go? Oh, put it into the wrong module. So let me move it to the right place. Okay, parameter and local variables, and then move this one also up back to that location. Below. There we go. Okay. So now everything is in order. Parameters and local variables is the module that you kind of need to read, okay, just to get conceptually what is going on. And then the zip file contains the C file, the annotated assembly file, and the trace. And then swap-stripped.ttp-asm contains the undocumented, uncommented version of the same assembly file, so that you can basically go through that and add your own annotation. And pictures are really helpful too, so you might want to get a piece of paper on the side just so that you can kind of track down, how the registers are changed and how they point to different things as you execute the code. Is that okay? All right, cool. So the next thing we need to do, according to this, is we have a new lab. Parameters and return value is a new lab. So we'll go over that just so that by the time we get to the lab, you guys kind of know what to do with it. So let's go ahead and do that. There's really nothing new in this particular lab, kind of the stuff that we have talked about already up to this point. So question number 1 is really just a reminder of how we return scalar type as a return value. Most return types of subroutines are scalars, such as integers, addresses, and so on. These types have a fixed and small size, and as such, scalar return values are usually passed to the caller of a subroutine via a register. So the convention that we use in this class is register A within the register bank. Most compilers have a convention of which register to use to specify the return value. So blah, 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 okay, we know the 5 subroutine and how to return the constant of 5. So that part we have already talked about in the previous class, because when we talked about subtract, we definitely have talked about this. So given that this is how a return value is specified, what is the value of register B after the following code executes, assuming 5 is defined as above? So 5 is defined the same as here. And the question is, when this code concludes, what is in register B? That's basically what it's asking. So now you have several ways to do this. You can copy and paste the code, put it into the assembler, assemble it, download the opcode, run it in the simulator, and find out the answer. That's one way to do it. The second way to do it is longer, but I think it is better from the perspective of understanding the material and give yourselves a chance to basically study, to practice, okay? Is not to rely on the simulator first, okay? But to go ahead and analyze this code manually and track down the execution of this code to figure out what register B should be by the time we get to the halt instruction. Once you have a theory and go like, I think that value should be 67, okay, let's say. Then you can run it in the simulator and see you get the same result from the simulator. If they match, it's a good sign that you have a good understanding of the material. If it doesn't match, then you have to kind of find out, why is it different? Where did my understanding deviate from the actual behavior of the processor? Okay, so that is why I personally would like you guys to do it the slow way and just manually track down everything, but it doesn't stop people from just copying and pasting the code and just let the simulator figure it out. Okay, so this is one question, and the answer is just a number, so I'm going to use 67. which obviously is not the right answer. Question number 2. While most return values are scalar and there's only one per invocation of a subroutine, the number of parameters vary wildly depending on what subroutine is being called. As a result, it is not a good idea to use registers to pass parameters, and most compilers use a stack to pass parameters. Because a parameter should not be specified before calling a subroutine, it is pushed on the stack before the return address is. So that's why you see that picture. You have parameters, parameters, parameter, and then the return address. Okay? After a subroutine returns, its parameters are still using stack space, and it is up to the caller to deallocate space used by a subroutine that has returned. So we have a subroutine call, kind of a sample call here. So XYZ is called with the value of 5. So from the caller's perspective, this is how it's done. The most important part here is after you get back into the caller, you have to increment the stack pointer once to deallocate the parameter that was pushed earlier on the stack. Okay? Now, not doing this may not be a big deal if you have one single function call in main, but it is a big deal if you have other things that you have to do after this, and particularly if this code is inside another subroutine, not balancing the stack is going to lose track of the return address. Okay? And that is usually a bad thing to do. Okay? So note that the return address is consumed, popped, and used by the called subroutine, and so the caller does not have to deallocate the return address that was pushed on the stack. In the previous code, at the entry point of the subroutine XYZ, what is the argument 5 relative to the location pointed to by register D? In other words, I'm asking you how many bytes is the 5 on the stack off of the location pointed to by register D. So let's say register D is pointing here and the 5 is here. I'm asking you how many bytes are in between. Now, if register D is pointing to that byte of 5 on the stack, then the offset is 0. If 5 is 1 byte above, the offset is 1. If 5 is 1 byte below, the offset is -1. You should never have an offset of negative something relative to the stack pointer, because anything below what the stack pointer is pointing to can be modified by interrupts. It's just that this processor doesn't have interrupts, but in general, interrupts will modify everything below the stack pointer, or what it points to. Okay. Question number 3. Arguments are pushed on the stack by the caller. How does a subroutine access those parameters? So the typical way that I do is to have another register C, to help me navigate on the stack to find the things that I need to find on the stack. The relative position of a parameter compared to the location pointed to by the stack pointer stays constant. In other words, the stack pointer is how we get back to the parameters. So this is the code from before. This is the actual call from the caller's perspective. In the subroutine XYZ, right at the entry point of the subroutine, in other words, right the first opcode that we execute in the subroutine, what does the stack pointer point to? This I have repeated quite a few times just in today's class. So it is just one of these choices here. Question number 4. Again, refer to the caller code as follows. So this is the same caller code as before. Set up 5 as an argument, push the argument, push the return address, come back, and then deallocate the argument. Let's say subroutine XYZ is defined as follows in C. So this is just a subroutine. It doesn't do a single thing. Okay, it doesn't do anything that is useful. Whatever you pass as a parameter, it just returns that. Okay, so it doesn't do anything really particularly useful. What value should we fill in the following TTP assembly code to implement this subroutine? In other words, I'm asking you, if I confine your code to be something like this, and the only thing you can change is whatever is in underscore, what should that be in order to implement that C subroutine? That's basically what I'm asking. Okay, it's going to be a number in base 10. So I'm just giving you a very typical incorrect answer. -6, okay? You will see the 0.0000, after that, that's just a canvas thing that I cannot stop. But it's just a number, okay? It really is just a number, so that this piece of code is going to do exactly what the original C code is supposed to do. Is that okay? All right. Question number 5. In the case of multiple parameters, the first parameter is pushed last. Consider the following C code. So in this case, we have sub1, which is just the name of a subroutine. I'm passing 2, 3, and 4 as arguments to that subroutine. So in this case, the parameters, the arguments are pushed in reverse order. So 4 is pushed first, and then 3 is pushed, and then 2 is pushed, and then finally, we have the return address pushed, which is these 3 instructions, and then we perform the call, and obviously we need to adjust the stack pointer when it returns. When accessed, but the point of this particular question is not to balance the stack, but when accessed from the call subroutine XYZ, how does the address of the first parameter relate to the address of the last parameter? So we are looking at the addresses of the parameters, not the values of the parameters. Okay? It is basically asking you, where is the byte containing this 4 relative to the byte containing this 2? And the answers are basically just describing the address of the first parameter is less than, the address of the first parameter is greater than, the relationship cannot be determined, the address of the first parameter equals the address of the last parameter. I mean, there are a few of these you can probably rule out pretty quickly. So your actual number of choices to really think about is not that many. Question number 6. Refer to the code in the previous question, and it's just repeated here, so you don't have to refer back to the question because I just copied and paste here. Assume the C protocol of sub1 is as follows. Okay, so we are passing 3 parameters and it's returning an unsigned 8-bit integer. Now consider the subroutine as follows. LDI A with 2, add 2 with D. What is A at this point? In other words, I'm asking what is register A at this point. That's what it's asking. Okay, now you have to be really careful to distinguish between the value of a parameter, what is the content on stack, as opposed to the address of a parameter, which is really just a particular address. So make sure you distinguish between those two. Okay, so this, once again, the important thing is you have to have a clear picture in your mind of what is on the stack at the entry point of a subroutine. So are we good so far? Okay, so this is your lab activity for today. I made it so that you can turn it in a week, which is a pretty long time, but I would try not to spend too much time on this one because this is really a practice on the topics that we have already talked about. Most of this stuff we have already talked about before today. Today was, the new topic of today was local variables. None of these examples involve the use of local variables, only parameters and return values, and also the return address. So are there any questions about this particular lab? No, no questions? Well, since we don't have any questions and we have 10 minutes left, I have a question. Can we do recursion? Exactly, that is the right answer. Why not? Okay, so let's try to do some recursive subroutine here. And we'll start with something that's relatively well known. Okay, Fibonacci numbers. And there are many ways to do Fibonacci numbers. There's a recursive way and there's a non-recursive way. But since the whole point of this lecture and also the 2 before that was to talk about subroutines, I want to do it in a recursive way. So I want to do it like this, and then we stop when the parameter is 1. Or 0. 1 is 0, 1 is 1. Doesn't matter. Is that okay? All right. So using this as our definition, let's go ahead and start writing the code. I may or may not be able to finish in 10 minutes because I also have to kind of explain along the way, but it would be a good way to start it. So we'll go ahead and write the C code first. Okay. Fibonacci numbers never get negative, so we can use uint8_t. So that means we can only work up to a certain number of Fibonacci numbers. So this is Fibonacci, and we have the first parameter. The only parameter is just n here. Okay. So according to this definition, I'll use this one here, because what that means is if n as a parameter is 1 or 0, we'll just return what that number is. So I don't need like 2 special cases. I just need 1 special case in that case. So we'll say in C code, we'll say if n is less than 2, then we just return n. This is also just not usually how I do things because I don't like to use returns inside a conditional statement. But it helps to simplify the code. So that's why I'm doing it like this. Otherwise, we do a recursion. Okay, and the recursion looks like this. So we have to call f again with n minus 1 as the parameter, as the argument. And then we have to call it again with n minus 2 as the argument. So is that okay? Are we understanding the translation between the recursive definition from a mathematical perspective to the actual code in C? So we're good? All right. So now the question is, given that is the C code, how are we going to implement it? So I'm going to save this, okay, because I have a feeling that I may not be able to finish everything today. So I'm going to say this is fib.c. And then we'll at least get started with the translation of this into assembly code. Okay, so to translate this into assembly code, the first thing we kind of need to do is to write it in the flattened C code first. Okay, so we'll go ahead and start with that. And I'm going to start to do it over here because I'll just kind of copy and paste this code. And each time we'll work on it a little bit. Okay, so flatten this means we will convert this into the negation to go to the else as a label. And since this won't compile, I'll make sure that it does compile. So else is no longer here. Instead, it is just a label definition, like so. And now that we have those definitions, we don't need the curly braces. Now, typically over here, I would have a go to go to end if, but it's not needed anymore because a return is not, there's no way you can continue execution after a return. So this will suffice. Are we doing okay so far with the flattened version of this code? Okay. We can flatten this a little bit more. In other words, we can look at this and go like, we can get rid of this and turn it into a greater than or equal to. But since it is greater than or equal to, we can now say that let's take care of greater than first, and then we'll take care of equal to. Is that okay? All right. So at this point, I cannot flatten this any further because the other way to look at this is 2 is less than n, which is something that is easy to do even in assembly. Okay, like so. Are we good so far? All right. Okay, so now we can go back to the assembly side and go like, okay, let's get started here. So this is f, which is the label of the subroutine. We know n is on the stack. We also know the return address is on the stack. And the stack pointer d is pointing to the return address right at the entry point of the subroutine. And there, I just answered one of the questions for your lab. Okay, some of you are nodding. It's like, yeah, we know that. All right, so next we need to do a comparison with 2. So, and when we have to compare to n, so I'll just do the usual thing. I'm just going to do a CPR CD, and increment C, increment C, so that C is now the address of N. And then I do a dereference, which is LDAC, so that A is actually N. And then we'll do a LDI B with 2 as a constant, and then we'll compare those two. So the compare needs to be kind of careful because we want to check for 2 is less than N. So we want to compare B, A, okay? And then if it is less than JCI, not JLI because it is unsigned, okay? So we do a JCI to the else label, and then JZI also to else label. Because the JCI takes care of the case when 2 is less than N, and then the JZI takes care of the case when N and 2 are the same. Okay, so this is how I take care of the comparison. So this portion is going to be the then case, and then we have else label here to clearly indicate this is the else case. What do we do when is a then? Well, the then is actually pretty easy. Whatever N is, we're returning it. And guess what? We already have parameter in register A, which is our return value register. We all set. Easy. And in order to avoid having, well, it's a toss-up, okay? Do you want to specify the return sequence of code twice or have a label to go to only one instance? The saving is not all that much, okay? So it's not a big deal whether you do it one way or another, but I'll just kind of go like, okay, let's go to one common end of the entire subroutine. So we'll say this is the end of subroutine F, and the end of subroutine F is here, and then we do the usual LD register B. Cannot use A anymore, have to use register B, increment D, and then JMPB. There we go. Okay. What about the else label? What do we do here? Well, in this case, we have to call F recursively. How do we call F recursively? Kind of the same usual way that we do things, okay? So we first have to retrieve what N is. N is already in register A, so that's kind of handy. So that means we just have to decrement A. So decrement A, so A is now N minus 1. Push it on the stack, decrement D, and store that on the stack. Then we have to save the return address, LDIA, with F underscore return as a label to return to. And then we push it on the stack as well, decrement D, STDA. Then we can call the subroutine. Which subroutine are we calling? F itself, right? So JMPIF. It is no different from calling any other subroutine, okay? When it returns, then we have to clean up that byte on the stack. But wait, do we actually want to clean it up? Let's find out what is in register A at this point and what is on the stack at this point. What is on the stack is the parameter, which is N minus 1, which seems kind of handy because we kind of have to pass N minus 2 to the next invocation. So I may not want to lose that yet, okay? But remember, the register A itself is not N minus 1 anymore. It is the result of F of N minus 1. So now I got two things on the stack, and one thing is kind of useful. The other thing one thing I can use right away. The other thing I kind of want to put it back on the stack and use it later, okay? So what I'm going to do is I'm going to do something like this, okay? So I'm going to do a LD B with indirect AD, so the B is now N minus 1, because I kind of need that back, right? But I'm not deallocating from the stack because I'm reusing that location to save register A, which is the value of calling F with N minus 1 as parameter. So I do another ST to D with A, so that now the whatever D is pointing to is F of N minus 1. Is that okay? It's a nasty little trick because without changing the stack pointer, D stays the same the whole time. But what I'm doing is I'm retrieving the content of what the stack pointer is pointing to into register B, okay? And then whatever register A has, which is the result of calling f with n minus 1 as argument, is now on the stack. So that's kind of the trick that I'm doing here. All right, so I don't want to push n minus 1 because this time I want n minus 2. So I'm going to decrement b so that b is n minus 2, push it on the stack. And then we have another return address to push on the stack. So we have LDI. This time I can use A again. F return 2. F return 2 is here. Decrement D. STDA. Then we can do the second recursive call to F. Okay. When it returns, let's clean up the stack. This time it really can be cleaned up. So we'll just go ahead and increment D. So this time we clean up the space used by the argument. And register A now has, I cannot clean up just yet, can I? No, this one, let's see. Yeah, we can clean up this one. So we can clean up the argument. After we clean up the argument, what else is on the stack? This thing has always been on the stack. What we did clean up was this. So that means the return value of f of n minus 1 is now pointed to by the stack pointer. The result of f of n minus 2 is in register A. And we just have to add those two up, right? So that means we can now do a LD B D, increment D. So we are popping f of n minus 1 to register B, and then we add B to A, and we're all done. Because at this point, register B has the value of f of n minus 1, but register A, we just came back from the subroutine, has the value of f of n minus 2. We just add those two. That becomes my return value, and then by following through this code, we just complete the return sequence code, and we're all done. All right? So let me save this so that we can talk about this next time. But this is basically, how you write a code in assembly. It's not really instruction by the instruction. There are definitely larger blocks of code that we use at the, we say, slap this block of code, because one block of code serves a particular purpose. So we'll save this, and let's head out to the lab.